Okay, good morning, everyone. Yeah, so today so fundamentally, I'm a sugar chemist. That's my core expertise. And more fundamentally to that, this is my particular sort of world leading expertise. I'm, one of probably two or three world leaders in the synthesis of these types of weird ass systems. So this is what we're going to talk about today is the thing that gets me really, really excited about all things in chemistry, and I do a lot of things in chemistry. So we're going to talk about C-glycosides and carbasugars. So next class, we're going to talk about why this is really relevant. So far, we've been messing around with normal sugars, right? We spent God knows how long talking about the importance of the acetal linkage in sugars. This is an acetal. It is an aldehyde that is masked as a diether, right? Through meter rotation, if you think about that, of course, this can't meter rotate because you've got an alcohol on here, not OH. But if you have an OH, it can meter rotate. Because theoretically, well, it's not theoretically, practically, this ring opens the aldehyde. If you go back, I think it's lecture 1. Cool. So this is the fundamental underlying feature. It's not a bug, it's like the feature of sugars. So one of the things that makes sugars awesome is that you can put them all together and then you have these enzymes, again, we're going to get to the next class, glycosyltransferases, glycosidases, which cleave sugars from things. They basically cleave along this bond. And it's not going to overly surprise you to learn that the way that enzymes do this is basically they're a source of H+. We get the external oxygen perfectly positioned. The whole thing gets twisted into a half chair in advance because the enzyme forces it that way. And it puts the H plus right next to that oxygen. There's no choice. So we protonate it. The whole thing has already been twisted into a half chair because enzymes cheat, basically. And you make oxocarbeniums, and then it's trapped inside an enzyme, and then the enzyme delivers a specific nucleophile, and you're off to the races. Again, we're going to discuss this in a bit more detail next class. But this is why how sugars are broken down in the body. Now, if you're trying to create a drug based on sugars, you don't want them to break down very quickly, so you need ways to stabilize them. And so far, everything we've talked about has relied on natural sugars, oxygen linkages, and occasionally we've swapped it out to activate them to do some chemistry, but we haven't talked about those as final products. Today, we're going to talk about a few final compounds which can imitate these. So there's two classes of these. We have the C-glycosides and the carbasugars. They're always treated as completely separate topics. I disagree strongly with that. I think they are essentially the same thing. So a C-glycoside is where replace exocyclic oxygen. And a carbasugar replace the endocyclic oxygen. So we have two different mechanisms for this. In both cases, we're disrupting the acetal. You no longer have an acetal, you just have an ether. So all the chemistry that enzymes rely on breaking this stuff down no longer work. but these adopt more or less the same shape as normal sugars. And so they have very similar biological impact. If the normal sugar is acting as a sensor or a receptor or a biomarker that's interacting with some other protein, these will interact in a similar fashion. At least we think. There's not enough data on that yet. It all looks good, but nothing's confirmed. So what I'm going to talk about today is a little bit about how to make these two different types of systems. And I think we're going to start with C-glycosides because in a lot of ways they're easier. So what's a normal way you can make a carbon-carbon bond? That's essentially what we want to make, right? We can start with like a bromine. So theoretically, what type of chemistries can you use for this? Either from a sugar class so far or from other chemistry that you know. Answers from both.
Just calculation, but I feel like that didn't answer anything.
Well, you are alkylating, but how are you alkylating?
With what is? Does it react with double bond? I'm thinking. Oh wait, that thing. Grignard agent.
Grignard, okay, yeah, you can use it. You can actually use a Grignard. This has been done. So what you can do is you can take magnesium. The yields aren't great, and you have to be careful about your protecting groups. And so you can insert magnesium bromide. And then you can treat that with an electrophile. I don't know. Something like that. Yeah, that works. Now you need to make sure that your R groups are probably benzyl protecting groups because they can't have carbonyls, otherwise you'll react with them. But not a huge deal. Not very common though, because the yields tend to suck. The thing tends to be very overly reactive. But that is an answer. I'll accept beta as well. Let's make that a squiggly line instead. Any other suggestions?
Uh, elimination first, then add to that double bond.
Oh, have you seen that before? Or are you just guessing?
It's kind of like a Glycoside.
Yeah. So you can actually, there's a really, really important way of doing this from the glycal. So we've seen the glycal. I wasn't actually going to get to this. This is very, very clever, Hazel, because this is relatively recent. I want to say like by relatively recent, last 25 years. So this is called a Farrier type 2 rearrangement. And so you can use a nucleophile. Common nucleophile used for this, we're going to use this a lot in the next little bit, is allyl TMS, where TMS is that TMS group, it's a silane. So if we think about that, essentially what we have is like it is a covalent bond, but it's very easy to have this as plus and this as minus. So it actually happens very similar. We're actually going to do an E2 prime with this. Note in this case, you have iota, an iodose kind of thing, compound. You'll have the alpha. So we don't need to get into the details of the orbitals. If you want, we can work it out, but I think that's of limited interest to this group. But you kind of you have to have the orbitals overlap. So equatorial gives you equatorial, axial gives you axial. So this is called, if you want to look this thing up, it's a Farrier. Sorry, this is just a Farrier type 1 rearrangement. Type 2 is something we'll talk about with the carbasugars. Okay, what I was hoping I was going to get the answers for would be ionic, radical, and maybe cross coupling. So we'll see a few examples of each of those. So let's say we have this kind of system. Let me try to do this right. Yeah. Very similar to the LTMS, it's just a slightly stronger nucleophile. This just does essentially an SN2. Similarly, you can use other kind of strong carbon nucleophiles, cyanide. I wish that worked a little better than it does, but it does work. Or malanates. You can't have it too strong because you start doing some weird acid-base stuff. So you don't normally use like methyl lithium or something. And this works for malonic esters as well, malanates or malonic esters. And for those who's been a little bit of time since you've seen this stuff, a malonic ester, really similar. It's just you have an ester on one side instead of diketone. And basically it relies on the fact that these hydrogens here are super acidic and are basically popping on and off like crazy. And so you can generate a C- at that position very easily and it attacks. These are all kind of not super strong nucleophiles. Super nukes destroy everything. So this is a good way to get beta. The problem with making alphas this way is these are kind of SN2 reactions, and the beta halides are not very stable. And so when you try and treat beta halides with these nucleophiles, bad things happen. They just kind of fall apart. They don't work very well. So it's a good way to get the beta. To get the alpha, what we generally want to do is radical chemistry. And I'd say the most reliable form of this uses some chemistry we saw in a deoxygenation lecture. So if you remember back to the deoxygenation lecture, a week ago, I guess, what we were using was AIBN and tributyl tin hydride, and we were putting a hydrogen onto things. Here we have, instead of a hydride, we have an allyl group. So again, if we think about what we want to do, mechanistically, we generate the radical from AIBN. It looks around for the weakest bond to generate. The weakest bond is this carbon-bromine bond, or carbon-tin bond. Again, just like we had the tin-hydrogen bond was the weakest bond, it's still this one. The butyl groups are unactivated. They're just normal carbon groups. This has an allyl group. This doesn't work with anything else. You do need to make sure that you have this because this bond is weakened, because you already kind of can stabilize a radical on this carbon with the allyl group. Whereas with the butyl groups, you don't have that capability because there's nothing there. So that's why you get selectivity for the allyl over the butyls. So this comes in, it steals the allyl group, and we generate the tin radical. Okay, now, again, radicals go after the weakest bond anywhere. The weakest bond is still the allyl tin group, but if this goes and grabs another allyl group, nothing interesting happens. You just kind of swap them out. So the second weakest bond present is this carbon-bromine bond. So this is exactly what we saw with the deoxygenation chemistry. So I'm actually drawing in the orbital that you're going to get out of that, and it stays intact. It doesn't flip. And it's because of the anomeric effect. It's not because it can't flip. It can. It just prefers to sit there. We say it's because of the anomeric effect. I don't love that argument because I don't see how that works. You can donate into, there's no bond there for you to donate into an antibonding orbital from. But I guess you can argue that there's some space, there's some electron density space up in here in a singly occupied molecular orbital, which allows for some interaction. Anyways, the radical is configurationally stable. I think what we're doing is we don't quite understand why it is stable. There's probably some good computational chemistry out there that I'm not aware of. But the truth of the matter is it just is. So we can wave our hands all we like to try and justify it, but that radical stays there. Now we've made a relatively strong tin-bromine bond. It's a nice strong tin halide bond. So that's good. Now we have a radical. It finds the weakest bond anywhere. That is the allo-tin bond, because it still is, because it's been the entire time. I have to say, it took me forever to understand radical chemistry. I still don't think I understand radical chemistry. But really, all we're doing is we're always attacking the weakest bond or the second weakest bond if we already attacked the weakest bond. And we've just stuck an allo group on there. And regenerated a tin radical, which can go find another bromide. Now, this is actually really, really reliable chemistry most of the time. Say most of the time because occasionally it fails. But you're really limited. You can use allo-tributyl tin. Like the only thing you can really put on there is an allo group. Nothing else really, really works. You can put a vinyl group on as well, but the yields fall off pretty massively. Now, that's okay. You've got a double bond, you can turn that into anything, but still a little frustrating. And I've turned it into a lot of things. This is probably my go-to reaction for these kinds of systems. But we can get a bit better than that. I'm going to say this is not my experience that this works very well, but other people have gotten it to work, so what the hell do I know? If you have benzyl protecting groups and you treat this with almost any carbon chain, I'm just going to arbitrarily draw one. Protected aldehyde. Can't use the aldehyde itself. Zinc bromide. In the presence of nickel chloride. And something called a pi box ligand. So just catalytic amounts of nickel chloride, which is great, except your ligand isn't as cheap as your nickel. All sorts of R groups. People are constantly coming up with new ones. They publish a paper saying, hey, our R group is better than other people's R group, but who cares? It's all the same. And what ends up happening here is this nickel kind of gets stuck in here. Nickel and purple. And this acts as a transition metal ligand, and I don't really want to get too much into the details of this. This is we're not. If you guys haven't covered cross coupling chemistry, you don't need to. It's called a Negishi coupling. You do want to look that up. What you basically need to know is you can use, especially iodides, works okay with bromides, any kind of non-electrophilic zinc bromide. You can't have aldehydes, you can't have ketones, you can't have really, really reactive C plus kind of systems, but almost everything else works. I would avoid OHs and NH2s as well, like acidic protons. So as long as you don't have anything reactive, you can stick anything on here you want. Nickel chloride, this ligand, and you snap that on. This is cross-coupling chemistry. As I said, works very well. Except whenever I've tried it. But I have been asking a lot of it. So we can make radical chemistry, we can do ionic chemistry, we can do this is ionic chemistry using the Farrier rearrangement, which was going to be kind of, it's slightly different because we're kind of moving this thing around. Note that what we've done now is we have this new double bond over here, and we can functionalize that using kinds of chemistry we have. And then we have the Grignard reaction that Hazel started us off with, which was ionic. So we have ionic, radical, cross-coupling approaches to make these types of C glycosides. Any questions about that before we move on? No? Okay. So that's actually the easy one. Carbasugars are quite a bit harder because if we think about the problem we had with a C glycoside, all we needed to do was essentially cut that bond and stick on a CH2R. And that's what we essentially have done. For a carbasugar, what we need to do is we need to kind of excise two carbon-oxygen bonds. This is considerably harder. So there's actually a lot less work done with it. I think I'm going to talk about a couple of my favorite approaches towards this, which I think are kind of the most elegant. So what we can do is we can sort of split them into two things. One, make from sugar. Two, don't make from sugar. They both have advantages and disadvantages. The advantage of making from sugar is have all other stereochemistry in place. So you don't need to remake all sorts of different types of stereochemistry. You have it kind of delivered to you because, oh look, you're making it from a chiral molecule to begin with. So if you want to make the carbon sugar of glucose, isn't it easier to start with glucose and try and find some way to cut this oxygen out than to try and make all the stereocenters of glucose. Well, yes and no. It can be easier, but it can be harder. The advantage of don't make it from sugar is don't need to deal with all those oxygens until ready. They both have advantages and disadvantages. We'll start with the top one now. And I think the best approach for this that I like is the C9E rearrangement. I'm looking for it in my notes. And excuse me. Let's say we have this molecule. Sorry, I want to make sure we have the right one. Okay. So there it is. So we have this. This is obviously kind of on our way. We sort of showed a couple ways we can eliminate a halogen at C6. And so we can have this kind of system. That's cool. So we can be able to access this. We've already looked at how to make something like this. What if we had a reagent that allows us to convert this to something useful? So I'm going to skip directly to the one that I think is the best, which is using, I could go through the history of all this and all the different ways I've been done doing this, but I don't care. I doubt you care either. So that's an isopropyl. I'm trying to draw it in instead of writing isopropyl. So there's titanium with one of those and 3 chlorides. Don't ask me how they settled on that as Lewis acid. This reaction, by the way, goes in 98% yield, which is just ridiculous. So what this does is it bridges this just means ligands. So there's N ligands on titanium. Chlorides, isopropyls, we're not really going to worry about it. So we get that. And strangely enough, you can lose chlorides from this, so it becomes neutral, which then actually, for a Lewis acid, frees up some electrons on the methyl. So we're actually going to go backwards a little bit. We're opening this the wrong way in a lot of ways. I'm going to put this in brackets because this doesn't actually exist, but that helps us understand the reactivity maybe a little bit better. and titanium is slightly positive. Then what can happen is this O minus here can now kind of associate with the titanium. Now, of course, it can't do it for net orientation, so what we need to do is we need to flip it. So what I've just done here is the titanium sitting down here, and it's now associating with, I'm just going to highlight that oxygen in red. This is why I hate Lewis acid transition metals, because they can just make way too many bonds to things. So we kind of have the titanium kind of bridging both of those, and this is still kind of slightly positive. But then what we can have essentially is this carbon chain closing in on that. So we follow that logic around. And if we sort of draw molecules in here, now all the other stereocenters, right? C3, C4, C2, and C3 are unchanged. We haven't done anything to those stereocenters. So we get to keep all the stereochemical information at those centers. Now we treat this with a little bit of water. Acid and water. We do the workup. What do we get? Well, we're going to cleave that titanium bond. We're going to cleave that titanium bond. That's going to generate an O minus. That O minus is going to immediately make a carbonyl. And we have that. So using titanium isopropoxide, chloroform, 98% yield. Very, very high yielding reaction. And what we've done is we've moved this oxygen, right, from being in the ring to being out of the ring, and we move the C6 carbon to being in the ring. We kind of swap their places. I think this is genius. You know, it hasn't really taken off, and CNIE doesn't get enough credit for the work he's done on these kinds of things, but this is just brilliant chemistry. The grad student who did this work is now actually a very successful professor in France. All the sugar chemistry is being done in France. But it's yeah, that's cool. Okay, but that's not a sugar, because hey, you've got a ketone there, and I don't want a ketone there, I want a freaking sugar. So what can we do? There's a bunch of things we can do. The standard thing that I would do in this situation is, use something called the Tebe reagent. And I have to look it up because I always need to look it up. There we go. I'll give you the structure, but you're never, ever, 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 ever going to have to give me the structure because it's stupid. It's one of those things where you just know they found out about it by accident. I'll tell you what CP is in a second. So it's got a chloride and a methane, like a CH2 group. Should probably just sketch in the CH2 at the back there. It's not completely obvious what that is. Bridging a titanium and an aluminum. One side has CP. CP is equal to cyclopentadiene, but negatively charged. Sorry, negatively charged. So that negative charge is in complete resonance with all those double bonds. It's very, very stable negative charge. And it kind of forms an interaction with the entire pi system with the titanium. I'm not an inorganic chemist. And the aluminum is there. And what we're going to basically do is we're going to transfer this CH2 and swap it out for the oxygen. And that's exactly what we do. You are definitely not responsible for the mechanism. You can look it up if you like. I like it, but it's just, that would just be cruel and beyond the point of the course for me to make you responsible for it. But that's where that CH2 comes from. Okay, so now we've introduced the double bond. Now we need to dig deep into our bag of tricks, and we're gonna actually walk through that bag of tricks on how to oxygenate that appropriately to get a sugar. And so for this, you need to step back into, that you're probably your first organic chemistry class where you start talking about activations of alkenes and different types of oxidations of alkenes. We want a anti-Markovnikov addition of water. And the way to do that is probably to use some sort of borane followed by sodium hydroxide, hydrogen peroxide. I'm not going to show the mechanism. You can find this really easily, again, because it should be in, if you kept your notes, hydroboration, deboration. Really want to draw a sugar there. I guess an OH at that position. And we've now generated a carbasugar. So we went from a sugar to a carbasugar. Now, you can see this isn't trivial stepwise, right? Like, we covered up a lot of stuff here. Yeah, this key step is one step, and yield is really good, but you got to make this guy first. And we've covered enough chemistry that you can now make that. Trust you guys are all able to do that. But it would take, 5, 6, 7 steps maybe from starting materials. It's not trivial. Then once you've made it, you do this reaction, which works great, and then you're all excited, but then you have a series of moderately yielding reactions to convert that ketone first to a carbon. You could also use Wittig chemistry or Horner-Wadsworth-Emmons chemistry if you prefer. And then hydroboration, deboration to install the hydroxyl group. So yeah, doable, but not trivial. And I have to say, I think this is the by far the best way to make this kind of thing from an existing sugar. So the other way that this does get done is, screw it, I'm not going to do this. I can assign my review article on this kind of thing if you and I'll post it. I'm not assigning it. You can read it if you like, but if you want another way, it's figure 18 in, let's try. So I'll post the article, but it's a really long review about cancer vaccines, and we'll basically see glycosides and carbasugars in cancer vaccines. And it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 step synthesis of a carbasugar from a sugar. Yeah, not easy. So you can understand why some people go, screw this stuff. I don't want to make it this way. I'm going to make it from something that's not a sugar. And yes, as convenient as it is to have all that stereochemistry preset, let's not and say we did. So there's two different approaches I want to cover here. The first one I'm going to call Hadlitsky chemoselective approach or chemoenzymatic approach. So I did a postdoc in this group. Did some of this chemistry. And what this relies on is the fact that you can take bromobenzene, stick it into an enzyme, or it's actually a bacteria, Pseudomonas putida, and it does a remarkable reaction. So it gives you a chiral diol of benzene. So why is this so remarkable? First of all, that is about the least stable form of this thing you can make, right? Like benzene wants to be benzene. You don't want a diene. You want to make it aromatic. So the thing this really, really, really wants to do is it wants to eliminate a hydroxyl group to regenerate benzene. So if you put a lot of energy into the system, that's exactly what happens. Now, if you're doing this under very oxidative conditions, what you tend to do is you tend to oxidize all the other double bonds. So if you normally have enough energy to react one of these double bonds with oxygen to break aromaticity, you have enough energy to break all of the bonds because the first one is the hardest to break. But this enzyme just stops here. There's, as far as I'm aware, this is the only enzymatic transformation that exists for which we do not have a synthetic chemistry equivalent. You cannot do this reaction using chemistry. There is a workaround that was discovered a few years ago by a group at University of Urbana-Illinois Champaign. It's clever, but it's not quite the same thing. And again, it's beyond the scope of this course. I just wanted to say it's not 100% true now as it was 2 or 3 years ago for me to say there's no chemical equivalent. I still say there's no chemical equivalent, but now there's a pretty decent competitor, which gets you there in the end as well. Anyways, the important thing about this though is that it's chiral. So you get one enantiomer. Why is that important? If you're going to make something that's going to be biologically relevant, you're going to put it into the body, you're going to make a drug out of that, you better only have one enantiomer. Otherwise, you're never going to get FDA approval, and you're not going to know what the other enantiomer is going to do, and all sorts of crazy shit happens. Okay, why is this interesting for making a sugar? Well, hopefully what you can sort of see is let's go back to what a carbasugar is. Now let's draw galactose for the sake of argument. And this gets us back to what a sugar is. And that's, I've drawn it that way, but I could have drawn it this way, right? So what we have is we have a 6-membered ring. We have a cyclohexane. And I know what argument I'm making. And it's got a lot of oxygens attached to it and carbons. And what we have up here is we've installed 2 oxygens, and then we have handles on all the other carbons. We have these double bonds that we can selectively functionalize. So I'm going to show an easy way to one of the enantiomers. To actually get the sugars themselves, the right enantiomer of the sugar is actually kind of tricky, but to get the enantiomers of some of the sugars is quite easy. So this bug, it's actually a really interesting example of bacterial evolution, in that in nature, it does not eat benzenes because there aren't many benzenes in nature. But in the last 50, 60 years, as we've started creating massive amounts of toxic waste, last 100 years, let's say, ever since about the 1920s, petroleum byproducts end up in landfill sites, we have tailings ponds, we have all sorts of things like that. Bacteria have evolved to basically eat our waste. So Putida has evolved to turn benzene and toluene into carbon. We have to mutate it to stop it reacting further, because what it's going to eventually do is break all the carbon-carbon bonds and generate carbon dioxide, because it's really, and draws energy from that. So we've had this bug that's evolved to live with human oil waste, which is really cool. So I'm going to start with a slightly different version of that starting material, which Putida also reacts with in exactly the same way. Group on top. Same thing, bromine, methyl group, methoxy group, methyl ester like this, doesn't matter. It does, the yields suck actually with this methyl ester, but you get only one enantiomer and it's got the OHs up. So let's take the enantiomer of this. So this is galactose. It's a carbasugar galactose, but I'm just going to call it galactose. The enantiomer will be called Ent-galactose. Or if you want to be fancy about this, you can call this D-galactose, so this is going to be L-galactose. Same thing. I'm just going to draw the mirror image of it. Okay, so what we can see there now is we kind of have the mirror image of galactose, and if I try and almost map atoms on, if we sort of follow sugar nomenclature, we can see that we already have the stereochemistry right at carbons 3 and carbon 4. We've got carbon 6 there in the form of a methoxy ester. And we have all the other carbons present. So we're already we've got 2 of the 5 stereocenters already set. So now all we need to do is make the other 3. So what we can do here is we can rely on selectivity and reactivity, and we can try and play with how we can make this kind of system. Okay. So this is where I want to spend a little bit of time talking about how we can functionalize double bonds. First thing we're going to do is we're going to get rid of these pesky alcohols, and let's protect them. And we can protect them by using, oh look, it's a diol. Shouldn't surprise you that we're going to use an acetal, just like we've been using with sugars. Okay. Now, let's just say I have any double bond. And let's say I have, something at an adjacent position. Anyone know how I can make that?
Can you do it in one step?
Yeah, one step, one reagent. How do you make a diol from a double bond? Cis diol.
Wait. I think Dr. Hayward actually taught us this.
Yeah, we teach it, and it should be in your introductory. It should be in the first organic chemistry text course you ever took. And I know for a lot of you that's a long time ago.
Wait, what? That one?
Well,
Nope,
I
not
think we
good.
talked
Can't
about that
remember.
too. But I'm sure for Hazel, back like in first year or second year back in China, you took this, and those of you from India, you probably in your intro organic chemistry course in undergrad, you saw this. And God, I know the U Windsor undergrads have seen this in their intro organic chemistry class because you either had Jim or I. Sorry?
Osmium tetroxide?
Perfect. Osmium tetroxide. The modern way to do this is we add in a co-oxidant, so you need to use very little osmium tetroxide. So 5%, and you'd use something like N-methylmorpholine. oxide as a co-oxidant. Regenerates osmium tetroxide. This is also called NMO.
I was struggling. How should I pronounce it?
It's good. Yeah. This works really, really well. Osmium tetroxide turns your pupils black and then you go blind. So you need to make sure you don't get any contact with it. It is reversible. You go not blind after about 6 months to a year, but you don't want to be blind for 6 months to a year because that kind of sucks. So you need to be very, very careful. It's also a gas. And it terrifies me that a lot of biology and imaging uses osmium tetroxide to stain cells and things, and they're just kind of really slapdash with it. And as a chemist, it scares me a lot as a reagent. Anyways, osmium tetroxide NMO gives us the diol. Okay, so why did I put it on the bottom face and not the top face?
Because of the steric.
Perfect. Absolutely, sterics. So it shouldn't surprise you that if I take osmium tetroxide, NMO, that we're going to react to do that. And if we flip back, we want both of those down. Now this one's a methoxy group. We can actually do that separately, but let's for the sake of argument, retcon the situation and say I just want to make the actual sugar. So I want it to be an OH. Got it, right? So out of curiosity, it's not out of curiosity, I guess it's out to make a point. If those are unprotected, you get attacked from the top face. Any thought about why that might be?
Hydroxide groups acting as direct groups.
Absolutely. So what's happening here is this hydroxide group is actually attacking the osmium, and it binds the osmium to the top face. And so the osmium then delivers its oxygens from the top face. Second question I've got then is why does this double bond react and not this double bond?
I know I don't have the answer to that because I was thinking of asking it.
Okay, any suggestions?
Electron, like, that's a double bond attached to, well, it shouldn't make that much of a difference.
No, I think I like the way you're thinking.
Because that's the only difference between these two double bonds.
Is what?
Like, it's attached to a, like, so it's the oxygen that makes a difference. Oxygen attached to the carbon.
What do you think about what do you think about the electron wealth or the electron density or the electron richness, however you want to talk about it, of the double bonds? Is the green double bond more electron rich or the blue double bond more electron rich?
The green one.
Yeah, The blue one is directly adjacent to an ester, so there's resonance into the ester, which decreases the electron density of the blue double bond. The green bond does have that resonance as well, but it's much further away. And so you have higher electron density in the green double bond. That is completely illegible. Okay, so why does having higher electron density make it more reactive? Do you know what the
Because
mechanism for osmium tetroxide addition is?
because the double bond is nucleophilic.
Yeah, in the addition of osmium tetroxide, you need the double bond to be your nucleophile. So if one of these is much more nucleophilic than the other, the nucleophilic one is going to react. Okay. So now all we need to do is we want this to be a CH2, and we want this to be a CH2 as well. So in this case, I'm going to give it as a freebie, because again, not really the entire point of this course. But you can sit down and start drawing the different chairs that you can get out of this and twist boats. What kind of reagent would you expect to transform that, to reduce that double bond?
Hydrogen
Yeah,
and palladium.
yeah. And then we just want to knock that down to the alcohol, right? And then we're done. Then we have our enantiomer of galactose. So how do we do that? I actually just taught this to my intro organic chemistry class last class. So they're whatever, 14 hours into organic chemistry. Nah, more than that, maybe 20 hours in. So reducing an ester to an alcohol. I know you know this, Ronaz, because I think you've done it. Or anyone else. Some hydride source. Maybe lithium aluminum hydride would be great. Or you could use sodium borohydride in heat. And you'll just reduce the ester all the way down to the alcohol. So I think that's actually the point I want to make is let's just take it. I just want one more example for us to be thinking about this. And I'll let you guys I'll give you everyone the benefit of the doubt on how this always opens, because it's actually pretty complex and you get a mixture, so we'll give away for free. So you have one equivalent of MCPBA, if you don't remember what that is. It's that weird thing, perbenzoic acid. Anyone tell me what kind of product it is? What does this do to double bonds? It's going to react with the double bond. It's going to react with the more electron-rich double bond.
Makes epoxide?
Yeah. Top or bottom face, you think? And so if I treat that now with a nucleophile, say methoxide, I would accept opening at either locus, and it depends, and we can basically tune this a bit, but I'd be fine if what you told me the product was this. Or rather, probably the real truth is and. So you can either get attack at this carbon or at that carbon. They're very similar. Electronics favors the one on the left slightly. Sterics favors the one on the left slightly. Electronics favors the one on the right slightly. They're pretty close. And when we've done this kind of chemistry, we kind of get mixtures 60-40, and we can tune it a bit by playing with conditions, but it's not very selective. So what this gave us is access to the cis, the trans diol. So the osmium tetroxide gave us the cis. Here we have access to the trans. Okay, there are lots of other ways you can make carbasugars. I'm not going to go through them. I think we have sort of two examples here, and I think that's good enough. I think we're going to leave it there. It's enough for you to get through the course material and see that these things exist. So next class, we're going to discuss enzymes, glycosidases, glycosyltransferases, and then we're essentially done with sugars, and we'll be moving into amino acids and peptides for the last month and a bit of the class. And biomaterials. So, okay, I'm done for today. Happy Wednesday, and have a good rest of your day.